Okay, in this video we're looking at 2021 paper 1 question 4. In part A, we're dealing with induction. We're asked to prove by induction that 2 to the power of 3n minus 1 plus 3 is divisible by 7. So our 4 steps in induction, they're always the same. Step 1, we need to prove that p of n is true for n equals 1. Remember that p of n simply means the proposition. Prove that this statement is true for n equals 1. When I sub in n equals 1, it becomes 2 to the power of 3 minus 1, which is 2 to the power of 2, and obviously 2 squared is simply 4. 4 plus 3 gives me 7. And I just need to prove that that's divisible by 7. It goes without saying, obviously 7 divided by 7 gives me 1. So the statement is certainly true for n equals 1. Step 2, I need to assume that the proposition is true for n equals k. It's not a whole lot you can do here. You just take your statement, instead of an n, you sub in a k, and we're just going to assume that 2 to the power of 3k minus 1 plus 3 is divisible by 7. And we're going to use this in order to prove that it's true for n equals k plus 1. Okay, so we need to use our assumption from part 2 to prove that the proposition is true for k plus 1. When we sub in k plus 1 instead of n, we get 2 to the power of 3 times k plus 1 minus 1 with a plus 3 here. Now, as always, what we need to do is try and manipulate this expression so it looks exactly the same or very similar to our assumption. In our assumption, we have a 2 to the power of 3k minus 1. So let's just multiply out this power and see what it looks like. When you multiply out your bracket, you end up with 3k plus 3 minus 1. I want 3k minus 1. So I'm happy out with this term and with this term. It's the term in the middle that I'm not particularly pleased with. So what I'm going to do is just rewrite this another way. I'm just going to rearrange them. I could write that as 2 to the power of 3 plus 3k minus 1. The plus 3 at the end is good news because it's there in the assumption. The 3k minus 1 is good news because it's in my assumption. This is the issue, the 2 to the power of 3. So I just rearranged them to leave the expressions that I like beside each other. Now, using the first rule of powers on page 21 in our maths tables, we can rearrange this. It's 2 to the power of each of these terms. And another way of writing that is 2 to be cubed multiplied by 2 to the power of 3k minus 1 plus 3. And certainly this is progress. 2 to the power of 3k minus 1, I want that. Plus 3 at the end, I certainly want that. The 2 cubed is all we need to play around with here. 2 cubed is the same as 8. So what I have is 8 times 2 to the power of 3k minus 1 with a plus 3. Now, I need to figure out how many 2 to the power of 3k minus 1s do I have in the assumption. Here I have 8 multiplied by this expression. But up here there's nothing there, so it must be the case that there's a 1. This is the equivalent to 1 times 2 to the power of 3k minus 1. So if I can get one of them, then I can just assume it's divisible by 7. At the moment I have 8 of them. Now, this is often a bit in class that students tend to struggle with. I want you to just think in the most basic manner. Let's say that I had 8 apples. I want to split these up. I want to give one of them to one person and keep the rest of them myself. If I have 8 of anything and I want to split it up, I can simply split up 8 apples or 8x into 1x plus 7x. The most easy way of thinking about that is if I give you 1 apple, I still have 7 apples myself. So 8, in this case, my apples are x's. If I have 8x, it's the same as 1x plus 7x. So same logic. If I have 8 times 2 to the power of 3k minus 1, in this case, my apples are the thing in the bracket. If I have 8 of them, if I give you one of them, I'm left with 7 of them. So I'm just going to split this up. 8 times this bracket is the same as 7 times this bracket, 7 times 2 to the power of 3k minus 1 plus 1 times 2 to the power of 3k minus 1. So all I'm doing there is I have 8 of this term on this line. Now I've got 7 of them plus 1 of them. That certainly makes sense. And now look what we have. The last 2 terms, 1 times 2 to the power of 3k minus 1 plus 3, I'm assuming that that's divisible by 7, so that one's certainly correct. And this one, the coefficient is 7. So obviously I can divide 7 in and the 7s will cancel. So what I'm going to do is just write this line up here and just conclude. So all we have to do is be careful to get the full marks by concluding properly. The last two terms, 1 times 2 to the power 3k minus 1 plus 3, that's divisible by 7 from my assumption. I'm just assuming that's true. And this one, the coefficient is 7. So obviously if I divided this by 7, the 7s would cancel. So the coefficient is 7, therefore it's divisible by 7. And now I can just conclude that it's true for n equals k plus 1. Let's look at step 4 now, writing a conclusion to explain induction. So when we're finished off induction, we always write this paragraph. Our proposition is true for n equals k plus 1 if it's true for n equals k. So based on the assumption it's true for this one, it's definitely true for the next number. But we proved it's true for 1, which means it has to be true for 2. And it has to be true for 3, and then 4, and then 5. And essentially that means it must be true for every single natural number. In B part I, we're given an arithmetic pattern. It's p plus 7, p plus 14, p plus 21. Essentially, it's just adding on 7 each time. And we're asked to get Tn, the general formula for this arithmetic pattern. Remember, when we're getting our general formula, you can go to your maths tables and the formula is there. It tells me that A is the first term and D is the common difference. In this case, clearly A, the first term, is P, D, the common difference, is 7. It's obviously just going up by 7 each time. So all we have to do is sub in. Instead of an A, I subbed in P. Instead of a D, I sub in 7. My final answer is P plus 7n minus 7. In part 2, we're asked to find the smallest value of P for which one of the terms will be 2021. Now, as far as I'm concerned, the easiest way to do this is to actually ignore part I and just figure it out, just think logically. Obviously, the term we're talking about is going to be P plus 2015, or it's going to be something like that. Essentially, how small could P be where I just add on a number, P plus the number adds up to 221. Just look at what they are. Like here, if P is 2, then this would be 2, this would be 9, this would be 16, this would be 23. And if I continued on, maybe I'll get to 2021 or not. Essentially, I think the easiest way to figure this out is to just take, right, it's 221. And each term is going up by 7 each time. So the term I'm looking for is roughly somewhere around 2021 divided by 7. And I'm trying to investigate, does 7 divide evenly into this? And if you plug that into your calculator, it doesn't divide in evenly. You get 288.7 something something, essentially. All I wanted to figure out was, right, that means that there's roughly 288 terms before I get to 2021. So let's just figure out what it would be as a whole number. I want to work out, if I just keep on adding 7 288 times, then what will this number at the end be? No, I'm not worried about the P yet. And I worked that out. So basically 288 multiplied by 7 gives me 2016. So if I keep on adding 7 288 times, eventually I'll have P plus 2016. And I'm trying to get to 2021. So obviously in this scenario I just need P to be 5. If P is simply 5, then the 288 term will be P plus 2016. If P is 5, that will give me 2021. So we end up there with P is equal to 5. That's our final answer for that one. So you can see there I didn't even use Tn from the previous part. Now it is possible to use Tn to work this out, but I think that's the easiest way of doing it. Just kind of looking at the pattern and figuring out, right, well, obviously if I have to get to 2021, it needs to be P plus roughly 2021. It actually ended up being P plus 2016. And then I can figure out, oh, well, obviously P must be a 5.